sir.
Okay. So only 10 students. What about the rest? You had a class before?
No. Yeah, join in.
Okay, let's wait for just a few moments.
Okay.
Okay, so let's start. So in the last class we have been talking about a particular partitioning algorithm which tries to partition the whole feature space into individual regions, okay, exclusive regions, we'll say this way. And now basically what we'll do, we'll see that in this particular class of partitioning methods, they have tried to minimize the criteria function. Okay? So here the criteria function is defined something like this. So that means, let's say if we have a number of clusters, so let's say in this whole feature space we have divided into two clusters. This is cluster 1 and this is cluster 2. So basically what will happen, we have to have a center point. Okay, so let's say this center point is here and maybe this center point is here. So now what they are returning with Ci means with center point. Okay, so let's say this is this center point. Let's say this. And what we have to do if we want to minimize the square distance, okay, that means for all the samples that we have, if we want it to be assigned to this particular class, the ith class, then the distance with respect to the ith class center should be the smallest. So this is basically the main equation that we see in this particular class of partitioning algorithms. and we'll be talking about two partition algorithm. The first one is the K-means algorithm, and the second one is the K-medoid or partition around the medoid. So up to this we have finished in the previous class. So let's see what the K-means algorithm is going to do. So though I have given the whole pseudocode over here, so just we have to keep focused on these two steps over here. So at the very beginning, what we have to do, okay, let's say this is your whole piece of space. You have a lot of data over there, something like this. And what we do, we have to randomly pick k points as the initial cluster center. So at the very beginning, you simply select a number of points as your cluster center. That's really random actually. So let's say if you have a cluster center here and maybe you have a cluster center here. If you have this cluster center, then really you will fall into this loop. What this will do? First of all, since we have, let's say we have defined this is my cluster center for class 1, this is a cluster center for class 2. Then what we have to do, we have to assign. So this is basically the assignment step. Okay, we have to assign the samples to a particular class. So as we have seen in the previous equation, so we want to minimize the distance with respect to the class center, right? Yes or no?
Yes.
Okay. So now if I ask you this particular question over here, let's say this cluster, so this sample, which cluster will you assign it to? Cluster 1 or cluster 2?
Cluster 1.
Yes. Why? Because the distance is small. So what we have to do for all the objects, so this is it, for all the objects or all the samples in that feature space, what we have to do? We have to assign it to the nearest cluster. Okay. So maybe it may happen that okay, these will be assigned to cluster 1, and maybe all these will be assigned to cluster 2. Yes or no?
Yes.
Then you can see that once the assignment has been done, the next step is basically we have to update the cluster center. Because if I look at this cluster 2, do you think the center should be at the side of the cluster? Yes or no?
No.
Then what should we do? We should update. We should update the cluster center. Since it is the K-means clustering algorithm, so how do we compute the new cluster center? We simply compute the mean of the samples. So let's say in case of cluster 1, if I want to compute the average, where will you have the new average? Where will you have the new average? What do you think? So do you think it should be maybe somewhere over here since I'm computing the average? Yes or no?
Yes.
So it means your new cluster center has shifted from the previous position to the new position. I mean, this is now the cluster center. The same thing we'll do for cluster 2. If I compute the center in terms of average, the mean, then where if I go, maybe it goes somewhere there. Now your cluster center for the second cluster is somewhere over there, right? Yes or no?
Yes.
Once we have this, now you can see that here you have a loop going on again and again, right? Yes or no? So that means now what you will do? Since your cluster mean has been updated, so the thing you have to recheck whether the samples they belong to the same cluster or not. For example, now if I look at this particular sample, previously it was assigned to which class?
C2.
It was assigned to class 2, right? Yes or no?
Yes.
But now once I want to do the reassignment again, because since our mean has been shifted, so we can see that this sample will now, it may happen like this, that this sample will now belong to this class, and all these samples will belong to this class. So once you can see that since some of the samples, they have changed their membership, so don't you think that you have to recompute the mean again?
Yes.
So in this case, what will happen? You again have to update the cluster. Since the mean has been changed, what you have to do? You have to again check for reassignment of the cluster membership, right? That means these steps will go on and on until what will happen? What's the condition? Until there is no further changes. Is this clear?
Yes, sir.
So this is basically what we are doing over here. This thing is very simple. First of all, at the very beginning, we randomly pick k samples as our cluster centers. Okay. This is totally random actually. Okay. And in this particular algorithm, the input that we have to give is basically, the tuning parameter that we have to control is basically the number of clusters. So let's say if I give the value of k is equal to 3, then what do you expect? You expect to have
3 cluster.
You can have k equals to 4, you can have k equals to 2, and so on. Now the question is that since it's an unsupervised method, do you know that which cluster number is going to be the good representation of this particular data set?
No, sir.
So we'll talk about this later. But is the algorithm clear? The k-means clustering algorithm?
Yes.
So let's just see an example over here. I'm just giving an example. Same thing. So if we have selected two random cluster centers, let's say this is this first cluster center, this is the second cluster center, and once we have computed the mean, then you can see the new mean. So the first cluster class membership was assigned. All these samples belong to this maybe cluster 1. All these samples belong to this cluster 2. So since we have defined the clusters, what we will do? We update the mean. So you can see that now the mean for cluster 1 has shifted over here, and for cluster 2 it has shifted over there. So once it has been shifted, so you can see that this particular sample, it belongs to this particular cluster 1, right? Let's see, this is cluster 1, this is cluster 2. So once you have updated the mean, what will happen? Once you go for reassigning the points, you will see that this sample, as you can see over here, where it has been assigned? It has been assigned to this cluster 2. So this step will go on and on until there is no further changes. Okay. Okay, so I just want to give a visual example, multiple visual examples over here. How basically you see that how the clusters are changing and the class memberships are changing, and at some point you will see that once you have reached the convergence point, okay, at the point where there is no further change, what will happen? If we compute the average, we'll see that the average is fixed at its previous position, right? That means the cluster center. So this is where we have found the clusters. And what we can see here, that k-means clustering will basically give you convex cluster shape. Okay, so you can see it from, since we're computing the distance, okay, so once you have reached to the convergence point, okay, so let's say you see that all the clusters, okay, they are basically convex shape like this one. Up to this, is it clear?
Yes.
Just a minute, I just have to fix small thing over here. Okay, now we have a particular problem in case of k-means clustering. You can see my screen, right?
Yes, sir.
Okay, so here we have a particular problem. This problem is that, so if we, since we have to initialize the cluster centers, okay, the problem is that if you initialize your cluster centers, let's say there are 2 persons, both of you have set the value of k is equal to 3. Now you'll see that 2 of you might end up with 2 different results. For example, let's say if we have the data like this, So what we see, we have seen that in case of the first case, let's say this is case 1, and let's say this is case 2. So what we see over here, now for person 1, whenever he has converted, his conversion result has ended up with these 3 clusters. Okay, that means this was the original data that you have over here. That means we have one cluster here, one cluster there, and maybe you have another cluster there, right? Okay. But for the second guy, what happened? Once he converts to his results, so what we have found, we have found one cluster becoming something like this. Okay. Another cluster has become something like that, and maybe another cluster has become something like that. Now the question is that, which one is the best case?
The first case.
Okay, the first case looks better actually. If that's the case, so what is the problem here in case of Kevin's cluster?
The loop will continue.
That's okay, the loop will be different, but the end result, okay, the end result is basically dependent on how you choose your initial cluster centers. Let's say for one cluster center combination, I mean, since we're talking about from the initialization point of view, you end up with something like this. With the same data set, if you run your Clemens algorithm second time or third time, what do you have? That means you end up with a totally different thing. Is this clear?
Yes, sir.
So that's why you can see that these 3 clusters, they have been showed here. This is for the first case, these 3 clusters. Okay. And then for the second case, you can see that here we have cluster 1, and here you have cluster 2 and cluster 3. Now, if I consider in a different way again, how about that? Why not that these 2 clusters, they belong to the same cluster? It should happen like that, right?
Yes,
Because
sir.
they are very much close to each other. And moreover, you can see that in this case, these 2 clusters, if you look from the previous example, these 2 clusters, they are very compact. However, this cluster is very loosely connected, right?
Yes, sir.
But you will see the difference. Like, since you compute your fitness function, your criteria function, you see that this one will give you a low value, this one on the other hand will give you a high value, right? Because for all these samples, they will compute a high difference, right?
Yes.
Okay. Another thing is that if these 2 clusters are very similar to each other, even in these cases, okay, in this it may happen that if you have to draw another example, it may happen that 2 of the clusters, okay, if they are very close to each other, I'm just showing from the point of the cluster centers, okay. So what we can do, we can simply compute the difference between the cluster centers again, okay. And if we see that if the cluster centers are very close to each other within a certain threshold value, if I write like this, certain threshold value, so what can we do? We can simply merge them together. So in this case, we'll have one cluster here, and then we'll have another cluster there. Is this understood?
Yes, sir.
So this is actually how you can sometimes take care of having too many clusters. But the problem is that if you have, let's say, few clusters, let's say originally there was 3 clusters. If I just draw like this, okay, maybe there were some other clusters there. But originally there was 2 clusters, but you have been assigning 3. That's the thing that you can solve using the threshold check. But how about you had 3 clusters? If I draw like this, you had 3 clusters, but you select the value of k equal to 2. In this case, what will happen? Maybe you'll have a cluster here, and then maybe you'll have another cluster over there. So keep this in mind. I will come back to this point soon. Okay, don't worry. Okay. So as I've said that different clustering algorithm can give you different results. So what should we do? So this is what we can do. We can run the K-means algorithm for a number of times. Let's say, for example, we can run the K-means algorithm 100 times. So you have your corresponding cost function or criteria function that you have computed for the different cluster centers. So in this case, how many different results do you have? You have 100 different results, and then since you want to pick the best one, so which one you might pick? You might want to pick the one with the lowest cost. Is this understood?
Yes, sir.
Okay, this is one way of doing it. Now, here we have a problem with the K-means algorithm. First of all, it has a chance to get stuck in the local minimum. As I've said that, as you can see from this particular picture. Okay, so it depends on the initialization. Given the initialization, basically you can come up with your own, own results. So that means you can get stuck in the local memory. There is no guarantee that you will get the best result, unless basically what you do, you run it for 100 different times, and maybe you come up with the best one, or maybe something that is close to the best one. Okay. Another problem is that it is very much sensitive to outliers. Can someone tell me why it is very sensitive to outliers or noisy data?
Because you have to consider the length is and
Yeah, we have to compute the average, right?
yes,
So since the average, let's see if I have two values here, and then one value is very far away. If I compute the average, what will happen? The average will be somewhere in the middle, right?
yes,
Yes or no? And basically, to take care of this sensitive or two extreme values, what we say the extreme values, normally another central tendency value is which one? We compute the mode, right? Or we can compute the median, right?
yes,
Okay. And also, as I've said, that K-means clustering, it gives you convex shape clusters. Okay, so basically this K-means algorithm is also not suitable for non-convex shape clusters. Okay, what does this mean? If I look at this particular example, okay, so the data that you see over here, so if we look at these two results from two different clustering algorithms, so you can see that this is basically the K-means algorithm which has defined the cluster. So the one cluster center is here, another cluster center is there, and all the blue point belong to maybe cluster 1, or the green red point belong to cluster 2. However, if we had used the density-based clustering algorithm, so what we can see from the density-based clustering algorithm, one cluster had a shape like this, another cluster had a shape like that. So in contrast to the previous result, which one is better?
convex shapes.
Yes, because we didn't consider, as I've stated previously, we didn't consider the continuity of the data. Okay, okay. Continuity of data means basically this is a dense shape, but it's a not convex shape cluster, and it is continuous toward this whole space, maybe something like that. But since K-means algorithm, we try to find convex clusters. What will it do? Maybe it will find a cluster center here. Maybe it will find a cluster center there. And then how do we define the class memberships? The closest members, right? So if
Yes,
we
sir.
look at these samples over here, so these samples is closest to this one, or is it closest to that one? Let's say if I write cluster 2 and cluster 1. So this region is
Cluster
basically
2.
close to cluster 2. So that's why you can see that this region they have assigned to cluster 2. See? So this is basically the problem with K-means algorithm. So in case of density-based clusters, okay, the K-means cannot basically define those clusters well enough. Anyway, so already we have talked about the problem of this K-means clustering algorithm. It is very sensitive to outliers. Okay, since it is very sensitive to outliers, so what should we do? Okay, so we want to take care of these extremely large values because it will distort and it will pull the mean towards it. So that's why we'll be talking about this K-medoid algorithm. So it is basically known as a partitioning panel, partition around the medoid. So instead of taking the mean as the cluster center, the basic difference is that what we're going to do, we are going to pick one of the objects, okay? Okay, we will take one of the objects as the center point. Okay, this reference point means it means the center point. Okay, so since we are taking the member as the centroid, that's what is known as medoid. Is this understood?
Yes,
Okay, that means in case of K-means, we compute the mean as the center of the cluster. But in case of K-medoids, what we do, we'll take one of the members. Okay, we'll take one of the members as the centroid of your cluster, and let's see how it looks like. Okay, so in this case, what we have. Okay, let's move to this next slide. Better. So let's say we at the very beginning we will arbitrarily choose k number of samples, but now the center has to be one of the members, right? So it may happen that we have picked this sample, and then we have picked this sample, and then we have picked this sample. Okay, so in this case, what we have, okay, so in this case, what we have, we will arbitrarily choose k number of samples, but now the center has to be one of the members, right? So it may happen that we have picked this sample, and then we have picked this sample. So it may happen that we have at this cluster center C1, and maybe we have picked which one? It looks a little bit different, right? Anyway, so they are showing it here. This one they have picked as the centroid of cluster 2. The same thing will happen actually. What we have to do? We simply have to check which samples are closest to the first cluster, right?
Yes.
So we simply assign the class membership depending on the distance, and maybe we might see maybe these, maybe what can I say? Let's say these two will go, or maybe these three will go to this cluster center, which is closest, and all these are basically closest to that cluster center. Okay. Once we have this class membership, we have to compute this criteria function E. Okay. Now what we'll do next? What we'll do next? We'll see that instead of taking this one as the cluster center, if I pick a new sample as the cluster center, what happens? So this membered selection is totally random. You see it's over here. This is totally random. So that means instead of this one, as you can see over here, if I draw with color, it will be better to understand. Let's say this was the earlier cluster center over here. This is the one that we see over here. Instead of the red sample, how about if I take the green sample over here? Can you see it? I'm showing it in this particular figure.
Yes.
So if I choose that one, okay, the thing is that you see that of course your cost function will change, yes or no? But let's say this is for the previous case, the cost was something like E, and let's say if we take the green one, of course your cost function, because you have to do the membership, class membership again, you have to compute this cost function, and you have got your new cost function E dash. Okay, let's consider it like this.
Yes.
Now which one is better? What do you think? How do you know that whether the new member as the center has improved the result or not? How would you know? Yes, by comparing between E and E dash. So if we happen to compute a function, let's say S equal to E dash minus E. So that means if E dash is smaller than E, of course, that means of course instead of the red one, the green one is better, right? To be picked as the cluster center. Yes or no?
Yes.
Okay. Now if we compute a function like this, let's say the value of S equal to E dash minus E. That means E dash means after doing the swapping of the cluster center, and E is basically the previous assignment, if we think like that. So if the value of S is less than 0, what does it mean? That means the new class membership, or you can define the new cluster center, it has improved the clustering quality. Can I say like this?
Yes.
Okay. But if it's the other way around, let's say if S is positive, what does it mean?
E is
Or if
better.
it is the red one is better, that means whatever the new one you have picked, the new one you have picked is basically giving a bad clustering result in terms of this cost function, or we can say this criteria function. Is this understood? So if the green one is bad, what can we do? So we have to randomly pick maybe another sample. Maybe we have picked this sample as a cluster center, and then we are checking whether it improves or not. Whether that means whether this difference between this criteria function is less than 0 or not. If it is less than 0, what does it mean? The quality has improved, right?
Yes.
Yes or no? And then this will go on and on. That means you have to randomly pick different samples as a cluster center, and then you have to compute the difference between their clustering quality. And if it improves, you continue. And at some point, if you check for all possible combinations and you have found that no combination gives you better result, then what should you do?
Should take that one.
Yes, that means that is the point where you have reached the convergence point. Is this clear?
Yes.
So that's why I have just written the pseudocode over here. The same way you have to define this k number of clusters. Okay. And what we have done, we have to choose these k objects from this data. It's not randomly. I mean, randomly you have picked a point. Yes, you did randomly arbitrarily pick a point, but that point has to be a member. Okay? I mean, it is something like this. It has to be a member. I mean, member of your data, right?
Yes.
Then the same way, you do this class assignment or membership assignment. Okay, you compute the cost function, and then what we do, we randomly pick another sample. Okay, as a cluster center. This means it's a sample you want to have randomly picked, and you want to see whether this one, if I pick as a cluster center, whether it improves the result or not. So how do we check? We compute the difference between the criteria function. So if the value of S, as we have seen before, that means the current cluster center was this particular object, and if you replace with this randomly selected member as a cluster center, if the result improves, then what should we do?
You should take the
Yeah,
old.
yeah. If it improves, we should take the new one, right?
Yes.
We should take the new one, and then the step will repeat again and again until there is no further changes. That means the basic difference between k-means and k-network algorithm is what?
In K method, you have to choose one, and then, but in the other one, you have to choose it randomly, and then just in K method, when you choose one, and then you do it, you choose another one again, and then you do it, then you see which one is improving.
So in case of k-means algorithms, if I write here it's k-means. So what we do, whenever we have a cluster center cluster defined, we always have to compute the center, right?
Yes.
But in case of k-methods, whenever we have defined the cluster membership, what we have to do, we don't compute the centroid, okay, as average. Rather, we have to pick one of the members. Okay, you have to pick one of the members as the center of the cluster, and then we have to check for the class membership and compute this criteria function. Okay.
Yes.
So it's very simple actually.
Yeah.
Okay. So now the basic question is that how do we choose the right value of k? That means choosing the right number of clusters. Okay. So for example, in this data, we can see that okay, two of these samples are two of the clusters are here, but someone might say that okay, here we have one cluster, here we have another cluster, right?
Yes.
Okay. So that's why what we will do, we have to run this k-means algorithm. Okay, we have to run this k-means algorithm for a different value of k. And of course, if you start with the value of k equal to 1, that means all the samples, that means all samples belongs to one class, right? So of course, it's not a good clustering method, okay? But still, if we do that, we see that for k equal to 1, you will have a very high cost function or criteria function value, okay? Then maybe if you try to increase the value of k, you will see that the cost function gradually decreases and decreases, right?
Yes.
So among all these values of k, which one is the best one? What do you think?
8.
You may say that 8 is the best one, right?
Yes.
Because you are saying in terms of the cost function, what does it give you?
Yeah.
It gives the maybe, but we know that if I have let's say these three samples, I give you these three samples. If I ask you how many samples the clusters are there?
3.
3 or 2?
2.
2, right? Maybe
Yes.
maybe one is here, maybe one is there.
Yeah.
But if someone says, okay, I have let's say I have these 7 points over there. Okay, but you can say that this is cluster 1, this is cluster 2. You can say like that. But if someone says that I have 7 clusters over there, and let's say this is cluster 1, this is cluster 2, cluster 3, cluster 4, and maybe cluster 5, cluster 6, and cluster 7. For example, I'm just showing you one of the extreme cases actually, but it won't happen like that. So don't you think your error will be equal to 0? in this particular example, don't you think your error will be equal to, that means your cost function, or if I say the cost function j will be equal to 0? Yes or no? Do you get my point?
The cost function will equal to 0.
Mm-hmm.
Um,
So how did we compute? The sample minus the cluster center, right? So
Yes.
this is your one of the sample, and the cluster center is exactly the same point. So how much difference do you have? How much difference do you have? 0, right? So if it happens for all the classes, for all the samples, how many samples did I give you? 7, right? Yes or
Yes.
no? I
Yes.
gave you 7, and you have defined 7 clusters. So in this case, in these extreme cases, what will be your cost function value?
0.
It's going to be 0. But do you think it's a good choice of picking the value of k equal to 7?
No.
So maybe you could have done, if the value of k was equal to 2, maybe that's a good choice, because here you have one cluster and here you have another cluster, right?
Yes.
So if I listen, J7 means if I take 7 clusters, and if I take J2, so of course the J2 value will be high, right? Maybe some compare, let's say some value of A that is not 0, right? Greater than 0. So now if you want to consider it from the point of the value of J, so you will say that, okay, the value of cluster value of 7 is better than the cluster value of 2. But basically, which one is better?
2.
2. Okay. So this is what we are going to do over here. So we are going to compute the cost function, okay, J, or let's say, or E, I would previously E over there. And we'll see that whether we have a significant decrease in the cost function, or we can say that whether the clustering quality significantly improves or not. Is this understood? And at
Yes.
some point, you'll see that if you increase the number of clusters, your cost function does not significantly decrease. It decreases, of course, it will decrease, but it decreases very slowly. So you can see that at the very beginning, your cost function was decreasing very sharply, or not exactly sharply, but very rapidly. And then at some point, your cost function was decreasing slowly. So basically, from this figure, we can find the elbow point, right? Yes or no?
Yes.
Like the elbow of your hand. So this is basically where you can say that if I pick the value of k equal to 3 at this elbow point of my cost function, this is basically the value of the cluster number I should choose.
Yes, sir.
Okay. But the thing is that sometimes you might not even have an elbow function or elbow shape like that one. For example, if you look at the figure on the right hand side, you can see that it is gradually decreasing, right? Yes,
Yes.
or no? So now the question is that where is the elbow? Here, there, or where?
We don't know.
Okay, but still you can do it, right? Because we know that if we compute the rate of change, I should pick a different color. Okay, if we compute the rate of change, okay, so you can see that the change here is what? Is this much, right?
Yes.
Yes or no? That means for the value of k equal to 3, if you compute the change, because in this direction of x, if I take this the x direction, or the value of k direction, so basically the change is always 1, right? 1, 2, 3, 4. You're going at the difference of step of 1, right?
Yes.
But we're looking at the changes that we see from the point of the cost, the change. Okay, so that is something like del of j, the change. But if we look over here for the value of k equal to 4, then if I look at the change, you can see that the change is less than the change that we have in the x direction, right?
Yes.
Okay. So this is how you can define. If you see the change in the, let's say if I define this is your y and this is your x. If the rate of change in the del x is greater than del y, I mean, you understand that basically you have reached a point where basically you have found the elbow point.
Yes.
So even if you go to the other point, let's say k equal to 5, so you see that you have a change like this. So even del y is even much smaller, right?
Yes.
So, okay. So but if you look at other points over here, here we have a large change for y. maybe here you have a large change of y, but once you reach over here, and then you try to get to see that the change of y is small. Once you see that this condition has flipped, this condition has flipped, you know that basically you have reached to your elbow point. Is this understood?
Yes. So now the elbow is which one side? The first one?
That is 3.
Okay.
Because you can see that once you go at, let's say, the value of k equal to 1, or at value equal to 1, you can compute the elbow point. Actually, you have to start with the point 2. You see that del y, the change in y is greater than the change in x, yes or no?
Yes.
Even for the point 3, the change in y is greater than the change in x, right?
Yes.
But once you have gone to this particular point 4, you see that for 4, 5, 6, 7, 8, you see that the change in x is greater than the change in y, right?
Yes.
But if you see the for other points, for 2 and 3, you see the change in y is greater than the change in x. So where is your elbow point?
3.
3. Because after 3, if you move to 4, it goes to that condition, right?
Yes.
And the same thing basically is applicable even for this particular example over here. You can directly see the change for 3, the change in y is greater than the change in x, right?
Yes.
But if you move to the point 4, the change in x
Greater than the change.
is greater than the change in y. So that means you have reached to your elbow point.
Yes.
Okay. Okay. And also sometimes choosing the value of k, basically it also depends on what kind of application you want to develop.
Okay.
And what does this mean actually? Well, it means that what we want to do here, let's say in the example they are giving, let's say you want to define the t-shirt sizes, okay?
Okay.
So let's say if you take, let's say 100 or let's say 1,000 people, okay? And from the 1,000 people, you measure their height and you measure their weight, okay?
Okay.
And then you want to define, let's say, the t-shirt sizes. Now, if I want to define only 3 sizes, that means small, medium, and large. So basically, you have to define from which group you want to define a t-shirt from them, right? That means if you define your group like this, maybe you can say, okay, for this group of people, I will build a t-shirt with the size of S. Accordingly, you have to define the measurement. And then for the medium size, this group will fit, can wear the t-shirt of medium size. And for this group, the people can wear a t-shirt of size L. And accordingly, you want to define the t-shirt measurement, right?
Yes.
But sometimes you may want to do it in a different way. Even. Maybe you want to, in your application, you want to say, okay, I want to have even, you have the same number of people, you have this 1,000 people, but now you say, okay, I want to have extra small, small, medium, large, extra large. So you can see automatically your class has been defined like that, right?
Yes.
Because that means basically what we have done, we just wanted to evaluate, not from the point of this criteria function or cost function E or J. Because if you want to define from the point of E or J, maybe we'll come up with something later. Okay, of course you have to keep in mind this one. But also we want to see how better your K-means algorithm has performed. It will depend on the application that we are going to design later. Is this understood?
Yes, sir.
So this is basically what we have in case of K-means clustering.
Okay.
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 Okay. So basically, this is the end of clustering. So we'll move to the next topic, that is support vector machine.
Okay.
So up to this, do you have any questions?
No, sir.
So can you see the screen?
Yes, sir.
So this is basically one of the slides I've just collected from the internet actually. So you can see the author who have prepared this one. Even this author from the University of British Columbia has taken the slides from another professor from Andy Moore. Okay, you can find the detailed slide over there. Okay, so today we'll be talking about the support vector machine. So already you know about the support vector machine, right? Yes or no? In the class, whatever we have been talking about is linear discriminant. Can you recall linear discriminant? Yes or no? Can you recall about discriminant function? How about in this figure? So in this notation, the notation is a little bit different. So we have already talked about this decision boundary. So let's say for this 2D space. So let's say if we have some samples over here, we have the samples over there, and then we want to find this decision boundary over here. So what we have to do, we have to find the equation of W1 x1 plus W2 x2 plus the bias is there, or we can say W0. This should be equal to 0, right? Yes or no? And then we had to find these values of W, okay, using the stochastic gradient or batch gradient descent algorithm, right? Yes or no? Hello, can you hear me? Okay. Now the question is that, as I've said over here, if I had picked this decision boundary, is it still a valid choice to classify this data?
Yes.
Okay. Because why it's a valid choice? Because as we have seen over here, okay, so for the time being, whatever this value of alpha for the time being. So we have already seen that once we have defined the decision boundary, we know that on one side of the decision boundary we have the positive region, on the other side of the decision boundary we have the negative region. And then if we have a new test sample, for example, if I give you this test sample x over here, we simply compute this our hypothesis function. Okay, so previously we have written this as h theta of x, we have written like this. Yes? Yes or no? Okay. So, and now we simply see whether this function gives you a positive response or whether it gives you a 0 response or whether it gives you a negative response. If the response is 0, what does it mean? The sample is exactly on the line, right?
Yes.
And if it is positive, that means the positive side of the line, it is a negative, it's on the negative side of the line. So for this particular sample here, what should happen? We simply have to compute. Okay, as we have seen earlier, we have to compute this W transpose X plus B, or let's say W transpose X plus W0. Same notation, I'm just writing a different way. Okay, or in some cases, we have even seen theta transpose X plus theta 0 equal to 0. All these things are basically the same. Okay, I'm just reading it for explaining purposes. Okay, that means we simply have to compute this value of z. So if we say that this is what we are computing z, if the value of z is positive, that means we simply have to take the sign, and accordingly we know which class it belongs to, right? Yes or no?
Yes.
That means let's say this class belongs to class 1, this is class 2, or I can write it in a different notation. I can write class 1, this is class 2. In other cases, what we did, our predicted class, it was basically, it belonged to either 0, sorry, and 1, right? Yes or no? Right? That means this is a positive class and negative class. So we also know that what we here, they are denoting here, the positive class is denoted by +1 and the negative class is denoted by -1. So if you want to have a predicted sample in that way, which sigmoid function should you use? Which sigmoid function should you use? You should use the 10 hyperbolic function, right? Yes or no? Did you understand my question? Because yeah, the 10 hyperbolic function will give you your update. If the value of z is there, And according to this function, your output value is in the range of +1 to -1. But if I use the sigmoid function, we know that the sigmoid function gives you a value what? In the range of +1 to 0, right?
Yes.
Anyway, so all these things I just mentioned because this is what we have seen in case of discriminant function, where we simply define a function which will give us the decision right away. Yes or no?
Yes.
Is it a generative approach or a discriminative approach, or is it a discriminant function? Which one is it?
Discriminate.
Discriminant function, right? It's a
Yes.
discriminant function. Anyway, so the thing is that now, as I've said before, if we look at the previous figure and if you look at the next figure, so you can see that the line is different, but all of them are a valid choice, right? Yes, or no? Then the question is that which one will you choose? So which one should you choose? Because all of them are valid. This one is valid, this one is valid. But the problem is that if we have, let's see if I show this figure later. Let's say if I have this sample over here, now if this is the sample that you have to classify, this X is the sample you want to classify, then this sample will be classified to which class? To positive class or negative class?
Positive.
Positive class. But if you have this line differently, let's say if you had let's say this particular line over here, so according to this line, this sample X is going to be classified to which class?
Negative.
Negative class. But as I said earlier, if I didn't give you the sample, you could have said that we could have said, okay, both of the lines they're okay, right?
Yes.
Yes or no? This is okay, even that one is okay.
Yes.
So this is what we are going to do in case of SBM. The SBM will what we'll try to do, it will try to have a decision boundary, that means that this decision boundary which will have the maximum margin, okay? So what does margin mean here? Okay, margin means that if you think in this way, that if you increase the width of this decision line, at some point you will see that it will touch a sample from the negative sample, it will touch a sample from the positive sample, and then it stop over here. So if you consider that width, okay, that width of line, then this is what we have defined as the margin of that particular decision boundary. Is it clear? Have you understood this one? Okay, so that means since we have a lot of, that we have seen over here, we have a lot of options for different lines. We can have their corresponding margin. For example, if I have this sample, this particular decision boundary, so you can see that can you have a significant margin over here? Yes or no? Maybe not much, right?
Yes.
Okay. How about the second line? Okay, I should have picked a different figure. How about this one?
Yeah, you can have.
Okay, I can have a margin which is a little bit, which is larger than before. Yes or no?
Yeah. Yes.
That means if I have a lot of choices, so each of this line will have its own margin, or we can say this width value, right?
Yes.
And which one should be the best one?
The one that have the largest.
Largest or the maximum margin?
Yes.
Okay. So this decision boundary, is it linear? Decision boundary, is it linear? Yes, it is linear, right?
Yes.
Okay. So we want to find the linear decision boundary, the one with the maximum margin. That's why this classifier is known as the linear support vector machine. Is this understood?
Yes, sir.
So after this, do you have any question?
No.
Sir, hello.
Yes.
Sir, let's say this line has a parallel line which is a little bit left or right. Then then that is what we will choose.
Okay. The thing is that, like what as you have said over here. Okay, I understand what you're trying to say. How about, let's say, the line, if I draw with a blue line over here, some little to the left, right? It's not exactly a line. Okay. A little to the left. Yes or no? So
Yes,
once
sir.
you are increasing the margin, you have to increase uniformly on both sides. Yes or no?
Okay, sir. Then I understand, sir.
And then the thing is that when is it going to stop? It's going to stop whenever it will touch one or several samples from the different classes. Is this clear?
Yes, sir, it is clear, sir.
So the thing is that if you have a line a little to the left, so you can't have a much larger margin, can you?
No,
So
sir.
which decision boundary is going to have the maximum margin?
The middle one.
The one that will try to maintain as much as large difference from both sides or both of the classes, right?
Yes, sir.
So automatically, if you have this line that shift to the left, since the margin will be less, what will happen? You want to find an alternative line, if possible, that can give it even a larger margin, right?
Yes, sir.
Okay. So this is actually what we have over here. And since we have this name, support vector, the samples which basically defines the margin, those samples are known as the support vectors. Is this clear?
Yes, sir.
So that's why this is known as support vector machine. The classical name is support vector machine. And since the decision boundary here is linear, that's why it is known as linear support vector. We can also have non-linear support vector machine. In this case, what should we use? We should use a phi function, right? Yes or no? Okay. So we'll continue in the next class, inshallah. So up to this, do you have any questions? Okay. So I'm giving you the link to your attendance. Have you got it?
Yes, sir.
Okay. Okay, so that's it. Thank you.